Now I want to talk about something called Heisenberg uncertainty principle. Which hopefully is going to tie all these observations we have seen. So let's think about what we know to be a wave. Like here is a wave. A wave. And it has just like this going back and forth. And it does this from minus infinity to plus infinity, right? And now if I ask two questions, like question number one. So what is the wavelength? I can just look and say, okay, this is the wavelength, right? This is lambda, which is well defined. I just look from peak to peak and done. And if I know the wavelength, from here I know P is equal to H over lambda. I also know P, right? So then P is determined. And now the second question. So what is the position? So where is this wave, right? Is it at this location? Is it here, or is it there, right? So if this is like an ideal plane wave, position is completely undetermined. So this was for a wave. Now let's think about like what we call a particle. But now hopefully we like came to conclusion that when we say particle, of course they have like some form and shape, but because they are like showing like interference effects, there must be some waves inside, right? This is what we know the particle to be. This is like a wave packet. Now I ask the same questions. Let me first ask the second one because I can answer that. So what is the position? And I can say it's somewhere over here. I don't know, some x naught. There is some uncertainty, but I can kind of like locate the middle of this thing and then say this is the position. But now the first question, what is the wavelength? Now this is like undetermined, right? Am I supposed to take this one? Am I supposed to take this one? And this is like not even like a real wave packet. Real wave packet is much more complicated than this. Even in the like fictional one I've drawn, I'm having a hard time to determine lambda. So lambda is undetermined, or because P is H over lambda, P is undetermined.
Pardon.
Uh-huh.
When you said what is the position? Position of the red dot, do you mean?
Yeah, I said like, okay, this is like some blob. It's like a ball. I can think of the position of a ball to be center of the ball. I just like nothing like really deep. I just had to choose something. If you press, we can negotiate. Maybe here is also fine if that's going to make you happy. It doesn't matter. But at the end, I can choose like a location based on the localization of this object, but I cannot choose its momentum. So this little cartoon shows us combining wave and particle nature introduce a conflict between X and P, and that's the essence of uncertainty principle. Here's what Heisenberg said. So uncertainty principle. So this was, I think, due to Heisenberg, 1927. It is impossible to know exact position and exact momentum simultaneously. Okay, that's the uncertainty principle. Any questions or comments? Now I want to think about this wave packet a little bit more carefully. So as you can see, a wave packet requires an infinite number of waves. So what I'm trying to say is, like, you have this thing which we call particle. Actually, you can decompose this, right? You can decompose it, like you can take a wave going from minus infinity to plus infinity, plus another wave going from minus infinity to plus infinity, plus another wave, something like that, and multiply them with proper coefficients alpha 1, alpha 2, and alpha n, and this is going to give you this one, right? So basically, I am saying that here is my psi of x, which is my wave function, and I can write it as a sum over different waves, and I call it alpha n. And typically the wave we have is you can think about sines or cosines, but for analytical work, it is easier to work with I kn times x, right? And I have different k's, different wavelengths. Is that clear? However, this is actually because in the free space I allow continuously infinite number of modes. I need to write it like an integral. So this is dk e to the I k x, and this alpha n, I'm going to call it, maybe I can call it g. Okay, let me call this g. These are all g's. Okay. So this is going from minus infinity to plus infinity, and this is, does anybody know what this thing is? Yeah, this is the Fourier transform. So let me give you a couple of examples of psi of x and g of x. So this is, let me give like that, maybe 3 examples. 2, and 3. So this one is psi of x, and these are all x, and x, and this one is g of k, and because g depends on k, I'm going to draw it as a function of k. Hopefully you are familiar. How many people know Fourier transforms? Right? So if you have never seen this, don't be scared. I'll show you what it is, but you won't have to take Fourier transforms in this class, I promise you. But if you can, that actually helps. So I can have like a very sharp spike here, for example, right? Very sharp spike. So that means like I have only x is equal to x naught, and everything else is 0. Then if you put this to integral, right? You can also write, of course, the inverse transform. Let me write the inverse transform. G of k is equal to dx. Typically, I like putting 2 pi's here. So the inverse transform is going to be dx e to the minus I kx psi of x. Okay. So this is forward transform, this is inverse transform. And if I put psi of x is equal to just delta function, right? Integral will be 0 for any values except e to the minus I k naught, k x naught. But this is just going to be like a plane wave, something like this, but in k space, right? This is like a wave, but in k space. I can do exactly the same thing. Suppose I put psi of x is 100% wave, right? Now I put e to the I k k naught times x here. And this, okay, maybe you'll learn it at some point, but this expression e to the ik integrated is going to give you what we call Dirac delta function. And what you are going to have is like a peak here at some k naught. And typically we have like something in between, which is kind of like a Gaussian. If you have like some nice distribution, this is Gaussian. If you take the Fourier transform of Gaussian, does anybody know? What's the Fourier transform of Gaussian? Gaussian, right? It's also Gaussian, which is nice. The Fourier transform is itself. Any questions? So maybe I can think about like, let's consider Gaussian, which is like a minimum uncertainty wave packet, right? Yes. Yes.
I just confused. You're trying to show us the uncertainty.
Yes.
And you plotted these waves and used Fourier transform to reach the answer.
I didn't reach yet, right? Right now I said, so why did I introduce this? Not for the uncertainty. I introduced this because a wave packet, what we call a wave packet, requires infinitely many waves. You have to superimpose infinitely many waves to get a wave packet. But the only way we do this is the Fourier transform, right? Otherwise, I don't know how else to superpose waves. And then if this operation is needed to get a wave packet, I said, let me give you a couple examples of this operation. Like, for example, if you take a single peak, this is like a perfect particle, you have this wave in the k space. So this is x space, this is k space. And you have the opposite way, right? If you have like a perfect k naught peak in k space, you have plane wave, like which is like minus infinity to plus infinity, full wave in the real space. If you have Gaussian, you have Gaussian. These are just examples. Right now, I didn't derive anything. I'm just
Getting us familiar.
yes. I think we are trying to be familiar with like the objects we are going to work. And I'm going to use Gaussian to show you the uncertainty principle. So let's consider Gaussian, and this is the minimal uncertainty. I think it is possible to prove that Gaussian is minimal uncertainty, but it's a little bit technical, and I think we don't need it. So you have to take my word. Gaussian is the minimal uncertainty wave. And what is Gaussian? I have something like that. Gaussian is like wave function, something like that. There's like, maybe I write the a times e to the minus x squared over 2 sigma squared. And sigma is a parameter, and it determines how wide my Gaussian is, right? So I have sigma here. And from our last lecture, we discussed what is the wave function. We don't know what wave function is, but we called it like probability amplitude. And if you take the square of it, psi of x square, this is p of x, right? This is the probability to find the particle at position x. Then I need to calculate this delta x, and delta x is by definition expectation value of x square, which we'll come to later, but now you don't have to worry about that. And expectation value of x squared, and you take the square root. And if you have ever taken probability theory, expectation value of x is defined by sum over all x, x, px. How many people knows this? How many people know this? Okay, if not, this is the definition. I think not very complicated. And because x is continuous, we just need to take integral rather than summation. Okay? And because Gaussian is symmetric, expectation value of x is 0, and all we need to calculate is x squared. But it is also very trivial to calculate expectation value of x for the Gaussian, and it happens to be 1 over root sigma. So I don't expect you to calculate that, but believe me, it's just one line of calculation. I just didn't do it not to scare off any newcomers. Now g of k is some other coefficient, and we said it is also Gaussian, and you can take the Fourier transform, and it's going to be minus k squared over 2, 1 over sigma square. Okay. So this is also doable. It's just one line of calculation, but I didn't do it because we don't need that. Then I can calculate delta k, which is k squared minus k squared. I think at some point, for example, this I know. Whenever I see Gaussian, I don't sit down and calculate expectation values because I know that's the result. And what you are going to find is like, okay, this is again 0, exactly like x is 0, and this one is going to be 1 over root 2, 1 over sigma. Right? Then delta x, delta k is going to be equal to 1 over 2 sigma, 1 over root 2, 1 over sigma. These sigmas cancel, and I have 1 over 2. Good. But real waves are not ideal Gaussian, and anything, like I said, Gaussian is minimal uncertainty, that anything else is going to have more uncertainty, then delta x, delta k is going to be bigger than or equal to 1/2 for everything we know in the nature. This is the uncertainty relation. Any questions? Hopefully you can remember that, right? 1 over 2, delta x, delta k. My experience is like nobody has any problem with this. It's like a very simple thing to remember. And if you miss like 1 over 2, that's fine. You can, sir, yes?
In which lessons do we know this?
I think in mathematical physics, at some point they are supposed to show you like Gaussians. Okay, they are supposed to show you the integrals. But my experience, nobody knows how to take integrals. That means nobody's showing you integrals, probably. But you are supposed to see it in the first semester of second year. And you are supposed to see, I think for probability, you don't need to see anything. I think this thing I wrote is high school. And Fourier transform, you are going to learn it this year. Now, let's use de Broglie So this is de Broglie. And if you remember, P is equal to h over lambda. And K is, by definition, if you remember, we introduced K as wave number, which was 2 pi over lambda. And I want to relate K and P. Let's try to do that. So P is equal to h over lambda, and I multiply with 2 pi and divide by 2 pi. And I'm going to have like this 2 pi over lambda is K. Then I have h over 2 pi times K. And here's the moment I introduce something nice that you'll have to use a lot. So we have h bar, which is equal to h over 2 pi, because we don't want to keep writing 2 pi every time we have to write this relation. So this is going to be h bar k. So this is P. Okay. Now I'm going to put this in the relation, uncertainty relation. So you can think about this as like differentials, right? If delta P is going to be equal to h bar delta k, right? You take the differential on one side, you can take the differential on the other side, and I'm going to put this in the relation above. Delta x delta k bigger than or equal to 1/2. Let me multiply both sides with h bar and h bar, but this thing is P, so I'm going to write delta P. And this is the more common uncertainty relation that we use, and that's used in textbooks. Any questions? Okay, so there is nothing special about X and P. If you remember, we also had the same game for E and T. We can repeat all of these arguments like Fourier, but it's fine. So the message is we can repeat all of these calculations like Fourier transforms and all that for energy and time. And all the arguments are unchanged. Everything just follows through. There's no trick. And you are going to have delta E, delta T. This is energy, time, uncertainty. Is going to be bigger than h bar over 2. So maybe I can box this in, and this is energy, time. Okay. So these relations happen to be very useful to solve problems. I think there are a couple of examples in your textbook. I'm not going to do that, but I want to give you like a very nice interpretation, and then I'll finish it there. Here's what we call Heisenberg microscope. Let's consider so-called Heisenberg. Actually, I don't have to call it Heisenberg. Let me call it just a microscope. And the microscope is something like that. I have, I don't know, some eyepiece, right? And here's my electron. And my electron is going with some velocity, with some momentum. And I want to determine, so what is the point of microscope? So the goal is to determine X and P to arbitrary precision. Okay? But for this to happen, light should come in, right? And hopefully it should come to the microscope so that we can see it. So, because of scattering, now we are familiar with this, right? Light scatters through objects as if it's like a billiard ball. and it changes the momentum of objects. Because of scattering, there'll be like a change in momentum, delta p. Like I said, we don't care about numbers. Let's just put relational equations, and it's going to be of order of h lambda. Remember the Compton scattering, right? This is exactly what we had there. And so this is the uncertainty in momentum, and the precision of position is limited by wavelength. So delta x is of order of lambda. Basically, with a light of order of lambda, you cannot look at anything much smaller than lambda, right? Exactly like double slit, right? The double slit, for you to get the resolution, the d should be order of lambda. Now, and here's the result. So I can have like better position, better resolution in position, better resolution in position. If I need that, I need to get small lambda, smaller lambda. But small lambda is going to give me small delta x, which is small delta x. But from the first relation, right, delta p is going to be huge because lambda is small, but delta p is huge, such that delta x, delta p is going to be bigger than h bar over 2. Or I can say, okay, I don't care about the position, let me determine the momentum, then I can take like large wavelength. What is large wavelength? Large wavelength is small energy. If the energy of the wave is small, the change in momentum is small, right? I'm just poking the electron with very like low energy light, like small lambda, then delta p is small, the other way, large lambda, small energy. But then, because of the first one, delta x is large. And again, at the end of the day, I have delta x, delta p bigger than h bar over 2. So this is generally like used to motivate us about the uncertainty relation, but there is like a caution. Unfortunately, this example is actually very misleading and incorrect. And the reason is quantum mechanically, particle does not have p or x. Particle doesn't have it prior to measurement. So it is much more provocative than what I showed you. So this one is a little bit harder to understand, but I'm not going to get into that. So basically, act of measurement gives rise to what we call these observables, like momentum and position. And before, if you don't measure it, they don't exist. Why? I don't tell you because I don't think anybody knows. Okay. Any questions or comments before I finish? All right, thank you.